Good afternoon, everyone. What we're going to do today is just finish off the idea of fractions, right? And we will do that by just going back to the last two slides that we did quickly, right? In terms of addition of fractions using an area model. And when we looked at that, this question here, 2 1/4 plus 5 3/8 that we did last week, and I was revising it a little bit. One of the things to recognize in that is that when we look at the denominators, one is a multiple of the other. Right? So we look at the level of difficulty even in the addition. Ideally, the simplest of the additions, whether it is mixed number, right, or not, is when the denominators are the same. And then when we increase in difficulty, is when one denominator is a multiple of the other, like in this case here. So in the first case, it would be like 1/5 plus 3/5, right? Because the same denominators. In this second case here, where we increase in difficulty, it will be where 4, right, multiplied by 2 will give us 8. So therefore, 8 is a multiple of 4, right? And so that's the level of difficulty that we increase in when we do the addition or subtraction, right? So let's go with this one. So 2 1/4 plus 5 3/8, right? So there are different ways to do it. One way is you can work out the wholes first, right? So we have 2 units and 5 units will give us 7 units. And then we have 1/4 plus 3/8. And there are different ways to do this. We did this earlier on, showing the idea of a box and being able to cut the box into 4 parts, and then adding it by cutting across, making the box, which was 1/4, into 2/8, right? And so forth. Right? So let's repeat it here so you can see. Right? So we can cut the box up. 1, 2, 3 lines will give us 4 pieces. So we could shade that here easily. And we can recognize that as 1/4, or 1 out of 4 parts. And we can do the same thing. The next box, we consider them as 2 separate boxes. And what we're trying to do is guide the student to recognize where the equivalent fractions are. So we cut it up into 4 parts. And if we draw a line across, right, it'll be 4 2s and 8 parts. And how many parts are we interested in? We're interested in 1 8, 2 8, and of course 3 8s. So what we're looking at is doing an addition of 1/4 plus 3/8. And if we want to now say, well, when we're adding, we want to make sure the denominators are the same. That's what we normally tell students. What we're really trying to say is, can we get equivalent fractions with the same denominator? So how do we do that? We can draw a line across the quarter, and what happens now? That whole green thing, it is 1/4, but now where we drew this line across, we subdivided the whole into 8 parts. So that 1/4 is really equivalent to 2 parts out of those 8. So 1/4 is equal to 2 8s. And therefore, we've shown, right, concretely, if you're doing it like that, or at least pictorially, how it is that the equivalent fraction of 1/4 is equal to 2 8s. So now what we're saying is we can replace 1/4, right, such that we have 7 plus 2 8s. 1/4 is 2 8s, according to the diagram, plus 3 8s. And if we have 2 8s and 3 8s, then we can add them up and simply give us 7 and 5 8s. Right? For students who are getting problems, you don't need to emphasize too much the ideas of 8s. We can even think about it like we have 2 bags and 3 bags will give us 5 bags. Right, so we've solved that. And remember, one denominator is a multiple of the other. Okay, so this is the level of increase that we're talking about as we step up the difficulty, the challenge in the idea of areas. So we did addition of fractions represented with the area model. We didn't need to go through the idea of the wholes. That was understood, 2 and 5 is 7, right? And we handled the proper fractions that were left. Let's go look at another one now, where we're going to increase the difficulty. So we can see 2 1/4 plus 1 2/3. Right? As we said, basically we have 3 areas or 3 levels of difficulty in terms of addition of fractions. One where the denominators are the same. The second one, which we just did, where one denominator is a multiple of the other. And then in this case, which is the third level of difficulty, where the denominators are completely different. And we still want to be able to see if we can link it. So There are different ways to do it. Some teachers teach that you convert the mixed number into improper fraction for both cases and then solve. You can do it like that. I want to do it conceptually and show the students that easily we can look at the whole numbers. We have 2 wholes and 1 whole, right? So that'll give us 3 wholes, plus we have the quarter still, and we have 2/3. So we want to be able to do that. And so we're still going to use the area model to show such. And you can have the students have these rectangles, cut them out for them, and then be able to draw on it easily and identify. Or they can fold it accordingly. So we're going to do the same thing. This is the same quarter from before. So we can cut it up into 1 line, 2 lines, 3 lines, which are going to give us 4 parts. And you identify 1 quarter. We have that in green. Simple enough. And let's look at the idea of 2/3. So we want to be able to break it up into 3 parts. But because, like just now, we talked about the idea of overlaying the lines, if these lines are what we have as horizontal, vertical, sorry, then the next lines we're thinking about is doing them vertically. So if we see this now vertically, we're looking at the second proper fraction, then it's cut 2 lines going across, means it's going to give us 3 parts. And if we have 3 parts, right, simply enough, we want to identify 2 out of those 3 parts. So let's bring it up as something blue. So that is 2/3. So we have 2/3 and 1 quarter. Looks a little difficult for students to recognize at this point in time, but we want to be able to show them the idea of equivalence, right? Without running down to the procedural approach of finding LCM. What we're trying to do is equivalent fractions. So can we change the first whole, a quarter, where it was cut, the whole was cut into 4 parts, into something where 4 and we have 3 as well. So let's overlay those horizontal lines across. So we have 1, 2 lines across. So we cut it 4 ways down vertically and 3 ways across. As such, how many parts do we now have for that first whole? We have 3 rows of 4, which is 12 parts. So this green part, which was a quarter of the entire thing, is now represented by how many of those small rectangles? There will be 1, 2, 3. 3 out of 12. So it says that 1 quarter is equal to 3/12. Right? And this shows our equivalent fraction. And now the same thing we're going to do with 2/3. We have 2/3, we have the lines there, and we want to be able to indicate that it's similarly going to give us something like 12. So how do we do that? We need to put the lines up, which are going up and down, or vertically. So we have 1 line, 2 lines, 3 lines. We're going to cut it into 1, 2, 3, 4 parts horizontally, and 3 parts vertically. So that whole is cut into 3 fours are 12 parts. So how many parts are shaded that are blue? 4 and 4, 8. So we have 8 out of the 12 parts is equivalent to 2/3. So it's also equivalent fractions. As such, we have now converted 1 quarter and 2/3 into something which is palatable, something which is easy for students to recognize because they have the same denominators. So what we did, if we remember the 3 levels of question, we took, when we did the second question just now, by putting equivalent fractions, both being 8s, it came back to the lowest level. In this case here, this being 2 different, completely different denominators with no multiples of each other, then we took that using equivalent fraction and brought it back down to the lowest level, which is where they have equivalent denominators. So now we could replace it 3. So all we're doing is changing it into a form that we can work with. So 3 plus a quarter is 3/12, and 2/3 is 8/12. So we have 3 of those small rectangles plus 8 of those small rectangles are going to give us 3 and 8 is 11 of those rectangles, 3 and 11/12. So one denominator is not a multiple of the other. Operation with 2 fractions is happening here. So let's go on now. And we're going to look at addition of fractions, but remember there are 3 models that we're looking at: the area model, set model, and linear model. So we looked at the area model just now, looking at different levels of difficulty of fractions that are being added. And now we're going to do the linear model to show this. So 1/2 plus 2/3. Simple enough, recognizing that these denominators are different, they're not multiples of each other. So if we're a linear model, we can picture the idea of drawing a freehand number line, identifying where 0 and 1 is, and we can get a benchmark, right? An average or an idea for the students about the middle of that. If we were actually using a cord or a string or a thin piece of paper, we could fold the paper and mark it and find the exact middle, which would be halfway. So we have 0, we have a half, we have a whole, and of course we want to extend it so students could recognize that if we're counting, so we have 0 halves, 1 half, 2 halves, 3 halves, because it's equidistant. So we want, in our question, we want to figure out what a half is, right? And we've indicated that, and let's do the same for thirds. So we repeat the line, and we try to fold it in 3 parts to get an average. So we have 1/3, 2/3, 3/3 as a whole, 4/3 accordingly. Why we want to show the idea of extending past the 1 is for students to be able to handle the questions and and build in a conceptual grasp of numbers which are greater than 1, which are still fractions, either whether they're represented as improper fractions or mixed numbers. So 2/3, we can indicate that with a red arrow there. And simply, what we want to do is be able to recognize that if we split it, right, with the bottom line, the whole was divided into 3 parts. So what we're going to do from 0 to a half, we're going to cut that into 3 parts. And then from half to a whole, we're going to cut that into 3 parts. And 1 to 1.5, we cut that into 3 parts, which indicates that we have, if we come from 0 to a whole, we have 1, 2, 3, 4, 5, 6. So each one is 1/6. So we can say 0, 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. Continue. So what we're doing here is another way of showing equivalent fractions. And similarly, can indicate, right, the same thing down below, because if we looked at the idea of the first line, we took a whole and cut it into 2 parts. So down below in our lines where we cut it in thirds, from 0 to a third, we're going to cut that into 2 parts as well. So we're going to put one line between 0 and 1/3, halfway there. And like we're bringing it up, and one line between 1/3 and 2/3, one line between 2/3 and a whole, and so on and so forth. So if we count from 0 to 1, it will have 1, 2, 3, 4, 5, 6 lines. Means we're cutting into 6 parts, so each part is 1/6. So we have the same equivalence fraction denominator 0, 6, 1, 6, 2, 6, 3, 6, and going on. What do we recognize from this? We recognize the half can be represented as an equivalent fraction with the denominator 6. And 2/3 can be represented as an equivalent fraction with its denominator also 6. So a half is 3/6, 2/3 is 4/6. So let's indicate this by little curly brackets here to show the distance of a half. And then 1 for 2/3, just 4/6. And if we adding them, putting one next to each other, right, then we're going to have 3/6 and 4/6, and that's going to give us 7/6. Okay, so we're going to look at the area model now. We have 2 1/4 plus 1 1/8. It indicated as 2 wholes and 1 whole there. That's 3 wholes. So why we're saying that is we can represent it that 2 1/4 is 2 wholes, which is 4 and 4, 8, and another quarter, 9 quarters. And 1 1/8 is 1 whole of 8 parts, and 1/8, and one more part, 9 parts. So we have 9/4 plus 9/8. We're looking at the idea of doing it as a converted into improper fraction rather than pulling out the whole number. So one of the ways we can look at it is if we are thinking about the procedural approach of quarters and how do we get to the point of 8s, 4, and multiples of it, 8, 12, 16, and so forth. And if we did it for 8s, 8, 16, 24, 32, and what we see that's the same is 8s. So it tells us something that we want to be able to, since one is a multiple of the other, we want to be able to convert each of those proper fractions, or well, sorry, in this case, improper fractions, to a denominator that is the same, which in this case is 8s. So we can say 9/4 will be something out of 8. So we're trying to use that equivalent fractions. So how do we go from 4 to 8? It's a multiple. So we multiply 4 by 2. And because it's a balance, it's an equal sign. Whatever we do on one side, we do on the other. So 4 multiplied by 2 will give us 8. So 9 multiplied by 2 will give us 18. So we can say that 9/4 is the same as 18/8. And 9/8, well, it is as is. We want it as the same denominator, so we just multiply by 1 or keeping it the same, however you'd like to look at it. And do the same on top. 9 ones are 9. So we can now replace those by saying 18/8, well, that was 9/4, plus 9/8. 18 plus 9. You could add it just as is, or you could unify it by having one common denominator of 8s. Either one will work, and you can write your final answer, which is 27/8. Okay, so 2 and 2/3 plus 1 and 1/5, just the same question we did before, but we're going to represent it using this idea of showing that we have wholes. We have two wholes broken up into thirds. So one whole will give us 3 parts, the next whole will give us another 3 parts, so that's 3 and 3, 6 parts, and we have 2/3 remain. So 6 and 2 is 8. 8/3 we're going to get. And we can do the same thing, right, for fifths. We have one whole, which is 5 parts, and 1/5. That's one more 6 parts. 6/5. So let's say we want to do it procedurally. We just quickly want to be able to say, well, what is the common denominator between both of these? We can look at the multiples of 3, right? And the multiples of 3 would be 3, 6, 9, 12, 15, 18, and so forth. The multiples of 5, 5, 10, 15, 20, and go on. And if you do it enough, you'll see 30 is common in both of them. 45 is common, 60 is common. You can use any of those. I've found any one will work. 15 is the smallest one. Well, I'll use 15. Smaller numbers, easier to work with. So what it means is we want to convert 8/3 to something out of 15. So we're trying to show the student, even procedurally, step by step, supported by some sort of concrete or pictorial representation. Remember, Jerome Bruno speaks about the idea of 3 modes of representation, and the symbolic being the most abstract. And some students will be fine with it, and some students need that support. And it's best to build concept. It would be good to introduce them to the enactive or iconic modes of representation. So that's what we're trying to do here, to even support your algorithm that teachers normally want to teach. So how do we convert the 3 to the 15? It's a multiple. So what are we multiplying the 3 by? We're multiplying by 5. And if we multiply by 5 in the denominator, 3 5s are 15, we do the same thing on top. And we say 8 5s are 40. So we were able to convert 8/3 to 40 out of 15. And the same thing with 6/5, right? As you can see with the list of multiples below, 5, 10, 15. So that's the third multiple. So 5 times 3, right? And that will give us the 15. And whatever we do in the denominator, we'll do in the numerator as well to maintain it being equivalent. So 6 3s are 18. So now we have converted 8/3 to something out of 15, 6/5 to something out of 15. So we can replace them and say 40 plus 18, which works out to be 58 over 15. And in the last example, we didn't bother to convert the improper fraction back into mixed numbers, but we can do it here. 58 over 15, and there are different ways to do it. Some teachers teach, well, take the denominator and divide it, right? How many of the denominators we can get into the numerator, 15 into 58, and so forth, and that's fine. Or we'll do it a little differently by bringing up the idea of a number line. And our students should know our 15 times table because teachers have taught them that when we look at the clock, the first set of ideas of clocks that are being taught talks about quarter turn, half turn, 3/4 turn, a whole hour. So quarter turn is 15, then 30, that's 2 quarters, 3 quarters, 45, and 60. So they should at least know the multiples of 15 up to at least 60 or even 75. So if we have 58 over 15, where will that lie? Will it lie between 0 and 15? 15 and 30, 30 and 45, 45 and 60. And we could say somewhere in there, it is. So how do we get to that point? Do we actually have 60 15s? No, we don't. So we have 45 of them. So that gives us 1 whole, 2 wholes, 3 wholes. And what's the remainder from 45 to reach 58? 13. So it's 3 wholes with a remainder of 13 15s. And that's a nice way in order to convert from the improper back into the mixed. So let's look at the idea of subtraction of fractions. And we use a set model. Remember our three models, right? Set model, area model, linear model. So 3/4 minus 1/6. Now, one of the issues that teachers have with doing this is recognizing what it actually means, right? So let's bring it up. That's represented by balls, and we have them as discrete balls, which tells us that each one of these are completely separate. And out of this set, out of this group of 4 balls, we are interested in 3 of them. And we could repeat by another 4, right? And why did we repeat? Because we want to be able to build a set where we could represent it in groups of 4 and groups of 6. In the first line of alone that we had horizontally, we could get a group of 4, but we could not get a group of 6. So we add another group of 4. So you have 2 groups of 4. Can we now find groups of 6 there? But we find one group of 6, but we'll have a remainder. So we're trying to be able to find full groups of 4s and full groups of 6 without any remainders. So maybe we need to add groups of 4 again, another group of 4. So we have 1, 2, 3, 4, right? And if we're seeing this now, we have groups of 4 when you look at it horizontally. Those are groups of 4. And if we look at it vertically, the first 2 columns will give us a group of 6, and the second 2 columns will give us another group of 6. So we're able to find groups of 4 in one direction, groups of 6 in the other. So what is 3/4 of all of these? So this here tells us 1/6. This tells us another group of 6. So we can see 4ths going across, 6 going up and down. So let's indicate what 3/4 is in the first row. 3 of the circles are blue and 1 has changed color. And if we want to maintain that, if we had 2 rows, then we'd have another 3 blue circles and 1 that's changed to orange. And if we included the third row, we'd have another 3 blue and fourth one being orange. So we can think of it vertically as saying we have 3 columns that are blue and 1 is orange. So 3 out of the 4, right? So 3/4 of all the balls represented there are blue. Now we would like to do something, which is to recognize that we want to be able to convert. So I'll show you the procedural approach. What teachers would say is, well, let's go find the LCM. So the LCM is 4, 8, 12, and so forth. So we wrote that 4, that was the first row, 8 was the second row, 12 is the third row, and if we added another row, it would be 16, and another row would be 20. And let's indicate the idea of 3/4, which we just said was the blue circles out of all the circles. So 3 out of 4, 3/4 is represented here by this square that's identifying them. So that's the set of 3/4. And what do we want to do? We want to minus 1/6. So 3/4 tells us that 9 blue circles out of 12. Easy enough, simple conversion. Now let's look at the idea of 1/6. So if we look at the first 2 columns where we have 6 of them, 1 out of those 6 circles is red. So that indicates 1/6 of the first 2 columns. And then 1/6 of the next 2 columns. So what that tells us, how many red circles are there in all? 2 out of a total of 12. So let's think about it this way. So if we are putting down columns, the first 2 columns will give us 6. The next 2 columns will give us another 6, which is 12. Another 2 columns will give us 18. Another 2 columns will be going across will give us 24. Right? So that's the way of representing it. So we're showing the procedural approach matching with the conceptual. So that when we're teaching the students, especially conceptually, we want to be able to show this, whether it's the set model or any of the models, before we jump into the procedure. So what it tells us is that 1/6 is really 1 out of 6 in the first 2 columns and 1 out of 6 in the next 2 columns, which is 2 out of 12. So we have 9 12s minus 2 12s. So let's bring back up the idea of 9 12s. That is what we had, just 3/4. And we're going to subtract 2 12s. So let's cross them out. 1, 2. So what are we left with? 3 and 3, 6, and 1, 7. 7 12s. So 7 blue circles out of a total of 12. That is solution. So one of the things that when you're thinking about sequencing this, right? Remember that you think of the idea of Gagne and the idea of learning hierarchy. What are we going to put in order, right? How do we build this topic out? Which models we use, right? So the idea whether it's mixed number, area model, fractions with different denominators, fractions with same denominators, fractions with different denominators, which are multiples of each other. Improper fractions, proper fractions, linear model, set model, unitary fractions. And these are some of the ideas that we have to think about in order for you to follow through in terms of how do we sequence what we're teaching in this. And this is only for, because this is 2003, for addition and for subtraction of fractions. When we go on to the next one, which is 3001, then we'll be doing multiplication and division. Right? So thank you very much, people. Have a good day. Bye.